I'm going to give a talk on a very kind of small portion of my work that I've been able to do. Life at LCO is Las Campanas Observatory. So there's a broad kind of speaking about adaptive optics and about the work I do with Steward Observatory. But this talk will kind of focus on a trip to Chile, Las Campanas, Chile, which is about 3 hours to the north of Santiago. So really the best seeing I've ever, experienced in the just naked eye in the world. So I'll start a little bit more generally, talking about who I am. So of course the biography part, what adaptive optics actually is, and hopefully by the end of the talk, I got you to understand what is happening on these pupils right here. Why we need adaptive optics, and then we'll kind of meter it back to talk about what LCO is and how astronomers actually travel. So we'll get a little technical, and then we'll bring it back to have a little bit of fun and see what we actually do when we're out, observing at a remote site. All right, so I grew up on the East Coast in Blairstown, New Jersey. I started attending Northwest Jersey amateur astronomer meetings in 2007, so I was 10 years old then. This is me at 10 years old with our old DOS telescope computer software system. We had a 25-inch Newtonian that we used that I eventually took data with for MIT and for Wellesley College up in Massachusetts, and actually published a few papers with a professor there, Dr. Steve Slidman. And in 2014, I'm pretty sure is the year, I came down to visit Barry with another club member, and we gave a talk about our asteroid work. So if anyone remembers that, you have a great memory, because I can barely remember what year that was. I went to just a normal public high school, North Warren, graduated 2015, and I graduated with a BS in astrophysics in 2019. This was my awesome advisor, Dr. Gary DeLeo, and he gives great talks as well. So if you ever need a speaker, I could get you in touch with him. He gives very animated talks. Sometimes it's almost like too animated, but he's wonderful too. And just kind of for fun information, that same club has since donated the 25-inch to UACNJ, which Barry was a founding member of, and we replaced it with a 50-inch telescope, which we're fairly certain it's the third largest east of the Mississippi. We'll have to do a little more research on that, but right now the secondary mirror is not operational, so it hasn't actually had first light yet, but we're hoping by the end of this year. Just like everything else, COVID has slowed things down. So what I do now, after graduating, I moved down to Tucson and became an observational specialist for the U of A down here in Tucson for the Steward Observatory's Center for Astronomical Adaptive Optics. And we actually shortened that to CHOW. So we're always saying we work for CHOW, as funny as that sounds. And CHOW manages a whole lot of different types of adaptive optics efforts that all are underneath Steward Observatory. But the large telescopes that I mainly work with are like the MMT telescope, which is now only one mirror, the Magellan telescopes in Chile, which is what I'm going to focus on towards the second half of this talk, and the Large Binocular Telescope, which is in Safford. And all of those have adaptive secondary mirrors that feed any kind of high resolution instrumentation. So if you've never been down to Steward, this was the original, I think it was 1927, this was built, observatory. Now the name Steward Observatory is more of an overarching, they have their hands in just about every astronomical endeavor there is. So this is our office building, quote unquote. And I just happened to get, there is two A-10s in this picture because there's a Davis-Monthan Air Force base there, and we're right underneath the traffic pattern for that airport. So this is a very common occurrence to have A-10s over the top of the observatory. And this image is actually underneath one of the adaptive secondary reference bodies that I'll talk about a little bit later in the talk. But when you don't have the mirror on, it makes for some kind of strange effects if you shine a flashlight up into it. These kind of like octopus type circles all over the place. So I think I can probably skip this slide. I made this talk to be good for a whole general audience. You know, if someone has never seen a telescope before, but of course we have a primary mirror, secondary mirror gets reflected to either a detector or eyepiece, but I have a good feeling all of you folks know what a telescope is. So to upscale that to, this is the Magellan telescope, the Clay telescope. The primary is about at mid-level here where this person is standing. The secondary, which in our case is adaptive, is up here. And then we have a tertiary diagonal that comes out to our wavefront sensor. So this just gives you a scale of how big telescopes are, when you get to a 6.5 meter primary mirror for reference of a person size. So just to give a little information on the large telescopes, since they're cool to see images of. The LBT is up on Mount Graham near Safford, Arizona, and that's up around 11,000 feet. So it really has these, type pine tree things coming up there. It's not in a dome, it's in this kind of funky looking enclosure. And it has two 8.4 meter primary mirrors, and it uses two adaptive secondaries, which are in a housing, which is this, however tall that is, I think at least 2 meters tall. And the secondary is just under a meter for this telescope. And some things that we, in our backyards when we're taking astrophotography images, we have our neighborhood squirrels that we have to deal with. But when we drive up the mountain, we have to sign a contract saying we will not run over any red squirrels because they are an endangered species. So every time we come in, we have to read this document right here. The Mount Graham red squirrel briefing, quite literally. So there's all kinds of strange things you have to deal with when you deal with large telescopes. The MMT telescope, which many of you probably remember as the multiple mirror telescope, is now one 6.5 meter mirror on Mount Hopkins. Sorry, I forgot the S. And this is just south of Tucson, still fairly high, 8,600 feet. And this telescope will have the MMT adaptive optics for exoplanets, which we shorten to MAPS program secondary, which is what we're working on in the lab just about 24/7. I think someone is almost always updating the software or working on it right now. And this is also in an enclosure. You can see a tiny little square up there. And this is an example of the MAPS secondary. You can just barely see how thin it is, and we'll talk about why that is, getting put onto the rest of the whole assembly of the adaptive optics. And then what we'll talk about in depth at the end of this talk is coming down to Las Campanas Observatory, where you have the two twin 6.5 primary mirrors. And either telescope can actually use the Magellan adaptive optics, which we call MAG-AO secondary mirror. The trip that I got to go on, we happened to use it on the Clay telescope, which is the one on the left. And these stairs are just about as steep as they look, especially at 8,000 feet. Everything takes a lot more effort than normal. All right, so what actually is adaptive optics and why do we need it, or why do we use it? So I think some of you were talking about it already early on, that the seeing is bad. So astronomers call turbulence that we feel in an airplane, we call that seeing. And that ultimately is just atmospheric turbulence. It could be even dome turbulence on larger telescopes or in smaller observatories. But the star starts out as this perfect pinpoint in space. We have to look through it, through this darn turbulence that the atmosphere creates and just happens to keep us, alive, but still blasted turbulence. The telescope sees it and it creates a fuzzy blob because the wavefront, so any of the light that comes through, is not perfectly flat. So you see something like that whole twinkling, that, twinkle, twinkle, little star, that's great, but it makes your star looks like this. This person happens to not be tracking very well either, but it's still, you can tell it's not perfectly a perfect pinpoint. You've got kind of shaking and wobbling going on. So adaptive optics works to take that twinkling away. So it basically measures the distortions in that incoming wavefront to compensate for them with a device, which is a deformable mirror. Okay. So this is just kind of another slide describing that. The incoming wavefront kind of looks however it will look, some sort of air mass of turbulence coming through. It will hit the deformable mirror, and we have a feedback loop that will send out a corrected wavefront. So when you have the adaptive optics off, you have something that looks like this. Magellan AO correction can correct at 1,000 hertz, and you can actually get 0.032 arcsecond resolution. So you can actually get binary stars, or in some cases, you can get planetary disks around stars. So that's the ultimate reason. We want to be able to see more of the things around stars. And all of our systems utilize adaptive secondary mirrors, but there are other systems that have deformable mirrors in other parts of the light path. One of them is actually called MAG-AO Extreme. I haven't worked on that project particularly, but that's supposed to be the next project that goes down to Magellan, and I think eventually to go to the GMT, the Giant Magellan Telescope, which will be at the same, not at the exact same site, but very, very nearby. So different sources of turbulence. You just have pure air mass and atmosphere up in here in the tropopause. But then you also have airflow that comes over the dome, just over the boundary layer. And you also have heat sources within the dome that can be creating issues. So while we're creating these adaptive secondaries and other instruments that might be at the low point of the telescope, we have to make sure that they don't create their own heat properties. So we have to do a really good job of keeping laminar flow, even just within the dome. So just as another example, a point focus, all the light rays would come to the focus perfectly, but with turbulence, the blur is created because they don't come to a perfect point focus. Okay, so how do we actually determine the strength of turbulence? So we have the incoming wavefront of the light all squiggled around because we have atmosphere to deal with. This R0 is the free parameter, and it does have to do a little bit with the primary mirror of the telescope. It's called your coherence length as well. And it's a distance over which the phase distortion has a mean square of 1 rad squared. That's just the definition. Don't stress too much about anything with the math. So R0 is like 15 to 30 centimeters at really good observing sites. And just a little more information on it, what your 1 arcsecond full width half max would get you. Now, we have an entire software system that actually calculates this constantly at 1,000 hertz. But it sets the scale of all the AO correction. So don't worry about memorizing this. It's all put into our software. That's the whole point. Our brains just can't really, function in this kind of state. But just kind of some things to think about is that R0 decreases when the turbulence is strong. So that's the CN squared term. It also increases at longer wavelengths. So with that really just you want to think about that AO is actually easier in the infrared than with a visible light. And one of the kind of cool things about Magellan AO is that they have a visible light camera that they're able to use adaptive optics with, just kind of paired with. R0 also decreases as your telescope looks down to the horizon because you have larger zenith angles. And really nice sites like Mauna Kea in Hawaii, they have a lambda of about 0.5 microns, which is like 10 to 30 centimeters. And this all ranges from night to night. And even just during one night, you have some kind of crazy air mass that comes through. You might have had good seeing at the beginning of the night, and then it turns to crap because some sort of, air masses come. So to tie this in with how it's related to the diameter of the telescope, if the telescope diameter is much larger than R0, the image size of a point source is about this lambda over R0, and it's much larger than the lambda over that diameter of the telescope. So you have to almost imagine it as a large seeing disk. So how many large disks of seeing are coming through as turbulence through your image path, basically. And what this all this kind of little high level stuff here boils down to is that any telescope really larger than 25 centimeters is going to have problems with seeing. So even your 8-inch telescope, that's why, and you guys know this as avid astronomers, you have to deal with seeing every night. So, and this kind of, you can tie it where even if you just use a higher power eyepiece, it just makes a bigger smudge. It doesn't, improve your resolution. So you really need adaptive optics to do that. And so here's just another example. Some of you may have heard of speckle interferometry. So it's another way you can reduce seeing. Cliff Ashcraft, if anybody has heard about him, he has a very good speckle interferometry for amateurs setup. But we do have an increase of speckles as D becomes larger than R naught. So you can kind of get that here where you're 1 meter, 2 meters, you have more speckles. And then when you get to an 8-meter telescope like the LBT, now it's all speckled out. So this also helps, or I should say adaptive optics also helps battle the speckle scale or the diffraction limit ultimately. All right, so to talk a little bit about the actual Magellan AO facility and how this all ties together, MAG-AO is a facility instrument. So MAG-AO is a facility instrument at a classically scheduled telescope, which ultimately means there's not a queue. So a lot of large telescopes have moved over to queue observing, where there's just one telescope operator. He has a whole list of objects for that evening. The astronomer isn't even there. They just take the data, they put it on some sort of giant computer with great data capabilities, and the observer could be halfway around the world and download his data, and he never has to go to the telescope. This instrument, you still need the principal investigator or the observer to actually be there and execute their own program. And because of the complexity of the AO system, some of us have to actually go down there to deal with the adaptive optics with the secondary ultimately. But the observers are responsible for preparing and executing their own. CLIO and VisAO are two separate cameras. CLIO is an infrared camera. VisAO is the visible light camera. And this is just an idea of with longer exposures, you can achieve 30 milliarc second resolutions, 30% strels, and we'll talk a little bit about what strel is in a little bit. And we've had about 35 MAG-AO referee science publications if you want to go and look them up. This is an image of putting the secondary on, or actually getting the crane, using the crane to get the thing on because it's so heavy. It probably weighs around 300 pounds, I would say, with all the electronics on it. And then this is it on the telescope. Okay, so this is a good image of, this is not of MAG-AO, but this is of the MAPS mirror, just because MAG-AO, we haven't taken the mirror off. But this is one of my colleagues, Richard Sosa, is cleaning up the very inside of the mirror. So I'm just going to stop screen sharing for a second because I actually have this actuator in my hands so you can get a better look at it and a better idea of what the size is. So on the MAG-AO mirror, there are around 400 of these little actuators that have a magnet on the bottom, just kind of a coil on the bottom. They have a electronics board to actually get the feed forward loop into a computer. And then this long heat pipe is essentially to draw any heat away from the magnet and from the electronics board and out away from the mirror. Because just like I mentioned in the beginning, this heat that gets created on the electronics board is another source of heat and another mini source of seeing. And then it connects just quite literally by a USB-C wire to a daughter card, which then goes to a motherboard and ultimately to another computer to actually complete all the calculations. So I'm going to go ahead and screen share again. So now that you've seen what it looks like a little bit more up close, the actuator never completely touches this mirror. So the mirror is only 2 millimeters thick. And on the back side, it has its pairing magnet. So they use bias magnets to actually move the mirror, microns of a movement. So you can't actually see it with your own eye. You can hear it. You can hear the electronics kind of buzzing while it's moving, but your eye can't actually pick up the movement. And it gets taken and put in this housing, so you can see the tippy top of the heat pipe on all the actuators, and all the cabling of the daughter cards and motherboards are all jammed in here. And eventually this gets a shroud on it so that you don't have any contamination. But since we're still working on it, it's still out in the open. So this is just a more up-close example of what the Magellan adaptive optics looks like. So, and I misspoke, I'm sorry. The MAPS meter has almost 400. The MAG-AO has 585 of these actuators on its surface, and they can move 1,000 times per second. And it also utilizes a 1 kilohertz pyramid wavefront sensor to actually sense the wavefront. And this is another example of, here's the secondary mirror, and it goes into the pyramid wavefront sensor over here, basically on the NASMIC port of the telescope. And Magellan AO was introduced in 2012. So adaptive optics is actually still fairly new. The first one in the United States was in 2002 at the MMT telescope, which actually is this exact same mirror that's in this image. And we're just refurbishing it and trying to get the software to run a little bit faster than it was in the very beginning. So now I'm talking about this whole wavefront sensor. What is a wavefront sensor? We use a modulating pyramid, which can operate at 36 to 400 modes. And ultimately, each mode is represented by one actuator. I think I'll talk about that in the next slide. But the way you actually get this into some sort of computer program is you have something out in the pupil plane that gets focused through the focal plane. The pyramid splits it into 4 what we call pupils, which gets put onto the detector plane. So this is what we'll see. And that very second slide that had those 4 blurry circles, those are called pupils. It determines the slopes, through the normal kind of slope method, only through computer software. And then it's put through what we call tons and tons of GUIs. You'll see more images of these graphical user interfaces for us to actually watch the turbulence move through. Okay. So to also just talk about what the MAG-AO guiding technique is, because we do not use a laser. Many places use lasers for adaptive optics, but we actually use the science and calibration star. So if we're on the science target, we're using the science star as our guide star. Sometimes we'll have calibration targets. That's also our guide star. So we're taking AO correction and tracking on the same exact telescope. Of course it's the same telescope, the same star. So in the inside of the wavefront sensor, we have 2 different cameras. You have one for CCD 47 is what it's called, that just gives us an image of the star. That way we can get it centered on the wavefront sensor, and it's split here to go through the pyramid. And this is where all of the pupil calculations are done to get fed to a feed forward loop. And this is what it looks like on a graphical user interface. This is what that detector plane looks like, these 4 pupils. And on the bottom, we have another interface. This is a video of every single actuator is represented on this purple, pink, white video or image here. And exactly what the turbulence is getting seen on the CCD39, or the wavefront sensor, is also getting plotted here in terms of force. So we always want to make sure that we have fairly low force on the actuators, because the mirror is 2 millimeters thick. If we have any stress, it could cause it to crack. So we have this running all the time in order to keep an eye on that. So this AO feedback, Did someone have a question? No? Okay.
We have some chats.
Okay, I can't see them. Let's see.
It says, why was the actuator frequency set at 1 kilohertz? Does a higher frequency produce better resolution?
Oh, good question. Okay. So if the software and the actuators were able to move that fast, so they were only designed to move at 1,000, 1,000 per second, the MAG-AO Extreme can run at 2,000. So it's ultimately dependent on what you designed it to be able to do in the very beginning. In theory, running it quicker would allow you to interpret the seeing faster. We just didn't have the capability for MAG-AO.
So it probably costs more money too.
Yeah, most likely. Just about everything is costly. Yeah, what else was in the chat? I wish I could see it. Let me see if I can find it. Oh, I see
It's at the
it.
bottom of the screen in the middle.
Okay, for me, it's at the top.
Oh,
I don't know
okay.
if it's a screen share thing. Okay, yeah, actually, somebody answered it perfectly right there. Gives best responsiveness, but costs more. Yep. What else? Water glove for myself. Okay. Oh, those are all earlier questions. Okay. I don't know what the NPOI is. NPOI. Susan, what is NPOI? Let's do a speckle.
The Navy Precision Optical Interferometer.
Oh, got it.
In
Okay.
Flagstaff.
Got it. That's amazing. Okay. All right. So I'm going to move the chat so I can see it now. There we go. Okay. All right. So what is the AO control loop? So we have two different types of loops. You have open loop and closed loop. And the names almost give away what they're doing. But if the wavefront error is measured before it has been corrected by the wavefront corrector, the operation is an open loop. So you're really not correcting anything. You're typically not taking data when it's an open loop, unless you want to do, intentionally poor data. So you typically wait until you're in closed loop, where the wavefront error is measured after it's been corrected. Such a closed loop operation. So when the wavefront errors measured are small, the errors in the measurement and corrected are more likely to end up being removed. So that's why the closed loop correction is the norm. So to try to put it in a diagram form, the light from the telescope has a distorted wavefront, hits the adaptive mirror, goes into that beam splitter, which takes it out to the high resolution camera and to the wavefront sensor, and that feedback loop corrects the next cycle of small errors from the last cycle and just keeps the control system keeps feeding it forward the entire time, giving us that high resolution correction. And you're correct, if we could, this is what's moving at 1,000. If we could do that at 2,000, it would be higher resolution, but we just don't have the materials to actually do that. And it's possible that is just too fast to move the secondary with these large actuators like this, because the Magellan AO Extreme is not a secondary mirror. That has a huge optical bench that gets put onto the side of the telescope instead, and has something like 32 optical elements to actually do that feedback loop. I'm not involved with that project, so you would have to go and ask Dr. Jared Nails about that project, but that's the gist of what I know about it. It's not an adaptive secondary. Okay, and I mentioned STREL before, which is ultimately just a measure of the quality of an optical image. So when there's very good performance for an AO system, more of that energy is in the core, so giving you that nicely focused light. So it's really just this ratio of the peak intensity to that of what the perfect optical system should be. So when you hear the word like airy disk or airy ring, that's what typically is associated with STREL, and you want them to be nice, perfect concentric circles. And the Strehl ratio is typically between 0 and 1, where 1 is a perfect optical image. So someone asked how the wavefront error is actually calculated. So this is all done through the software. I don't know I'm more of an operator. I don't know the ins and outs of how it's actually calculated. I wish I did, but that's what the software engineers do. So you would have to ask them. I'm more of an operator, have the gist of how the software works and how to actually set it up, but the exact measurements, I'm unsure of. So good question, but I wish I had a better answer for that. I'm not the software person for our system. But what I can say on that, and yes, a smaller and rounder star is definitely better. When we get the software, at least on our end, when we're operating, like for the MAPS program, we have these modes, which are essentially the number of predictable wavefronts that we correct. So what I've been doing is creating our modes for the MMT, the MAPS program, and they're all based off of mathematical Zernike polynomial. So you could Google this, and it's basically piston, which is like focus, tip and tilt, which are these guys, astigmatism, and coma, and it's just an infinite combination of all these polynomials here. And they end up looking like these kind of strange shapes, but we use those to predict, basically have as many predictions of the atmosphere as we can. So this is probably the best answer I can give, is that we at least have these predictions of the wavefronts that we tell the software, this is what we predict the atmosphere will do. The actual calculation behind it, you would have to go look up the math behind Zernike polynomials. And there's another Kolmogorov, I think, prediction that they use, but I haven't gotten to that part in preparing the MMT mirror. So I apologize, I am still kind of learning the software part of all this while I get to work on the MAPS mirror. So this is an example of what we're working on. You know, to build the software, you have to give it predictions, because otherwise it has no idea, you know, what it's talking about or what it's trying to predict. So that's what modes are. Okay, so just scientific advantages to using visible adaptive optics instead of just infrared. Most astronomy is actually done in the visible, but no adaptive optics science has been done on larger telescopes until MAG-AO. We do have better detectors, much lower dark current, you have lower read noise, not really as many bad pixels. You're off of the Rayleigh-Jeans tail, so stars have a much greater range of colors in the visible. So that was one motivating factor for Jared Males and Laird Close for actually designing this project. And you also have higher spatial resolution with visible AL. So otherwise you would require, you know, like a giant Magellan telescope size to get the same kind of resolution, you know, the 20 milliarc second resolution range. And this is just a theoretical, you know, 100% Strehl. So you're perfect. This is what that airy ring looks like. You have all these concentric circles around it. And then what was predicted for the MAG-AO system when it was first put on was that it would have 94% Strehl correction. So this is what their Strehl ratio calculations were for their optics. Check the chat, make sure nothing has come up. Okay. So just some key AO performance with that visible. Visible AO can produce even more moderate Strehls on larger telescopes. So you have better Strehl ratios. And below will just kind of outlines in rough importance the basic requirements to actually have a good visible AO system on that size telescope. So you have to have a good seeing sight just to begin with. So that's why this whole system ended up going down to Las Campanas, because their seeing is on average, you know, half an arc second seeing. So that's why it ended up getting put down there. Whereas the LBT seeing, if anybody knows anything about Mount Graham, we often have up to 5 arc-second seeing. It's actually pretty terrible. Sometimes our AO there just can't work fast enough and we can't use it. We're not quite sure why the LBT ended up on Mount Graham, but that's kind of a political, we could chat about that all day. But I've had plenty of nights on the LBT where we couldn't close the loop because it couldn't work fast enough to overcome just the pure seeing that was there. So you need, of course, a good deformable mirror and a very fast non-aliasing wavefront sensors. So you really need at least 500 actuators to have as many predictable modes of the atmosphere as possible. And you need at least 300 well-corrected modes for anything, a telescope larger than 6 meters. That's why this has 585 actuators, and the LBT has 672 actuators. And you also have to be very, very careful with even just low wind. So because it's only 2 millimeters, there is a very real chance that it can get pulled away from the bias magnets. Now we do have clips on the outside edges. So in theory, if it does get pulled away, it is supposed to get grabbed, but we do have wind limits on the telescope just because you don't want it to get blown away. And this image, or this video, I think Laird talks to it a little bit. So this is just an image, or a video, sorry, of what without the AO, so this is AO open loop looks like. So some object that they're on, you can kind of see the speckles, you can see just the seeing as it's wandering through the page. And then as he turns it into closed loop, it makes a nice pinpoint, has a slightly airy disk around it, but does a very good job of correcting. And then he opens the loop again. And I think he closes it again at the end. So you can see how quickly it actually recaptures and creates a nice airy disk. Okay. So all this requires years ultimately of lab testing. So I think they had this in the lab for about 3 or 4 years, and they had to work a lot of end-to-end closed loop with using the actual camera that they were going to use. And you also have to be very careful of the alignment, even just within the wavefront sensor, to make sure you minimize any non-common path optics. So ultimately, trying not to induce your own alignment issues by having kind of wobbly optics or just wobbly supports in your system. And then if you're trying to use an infrared camera simultaneously with a visible AO, which is, you'll get a 200% efficiency boost just because you have 2 cameras working together. And it also gives you a good contingency for poor seeing when you can only use near infrared, where you just can't get that visible wavelength spectrum. And this video, turn it off preemptively. It's a little bit longer, so I won't play the entire thing here. But I want to give you just an idea of how many interfaces there actually are to get this started. So you have just a pure commands page where you can kind of get a preset. So you've already lined up the star on one of your cameras, and the telescope operator has also already got his guider on your target star. So you have to start it here. You always check everything to make sure seeing is still okay, see how many modes you're actually operating with. And I'll kind of just zoom through this a little bit. These are all on YouTube. So he's centering the star actually there. And you center the star using what's called the base side stages within the wavefront sensor. So there just is an X, Y, and a Z axis that you just barely move the detector to get that star lined up. Since it is already lined up with the telescope and the guider, it's just fine tuning. So as he fine tunes it onto our crosshairs, then you start seeing it come into the detector plane and gets illuminated on what we call our pupils. So this is the camera that actually will use the slopes to create a correction and feed it through that feed forward loop. And let's see when he turns the loop actually on. I'll zoom up a little bit. These are all on YouTube. If you want me to share his YouTube channel, I can do that at the very end. And let's see here, come on. It does take about 5 minutes to actually acquire each star and get everything set up. So it's not like an instantaneous type project. I wish it was. You have to take a dark every time to make sure you don't lose anything. It calculates how well it thinks it will actually correct. And all that waving and wiggling that you see on the pupils is actually watching the seeing moving through. So you can kind of watch the seeing in real time. And I don't know if he moves over to that pink. I guess he does a little bit over here. Yeah, he doesn't have it on yet, but let's see. You can kind of see the seeing coming through. It's got to go to closed loop eventually here. And we're also keeping an eye on, there's Katie, one of the ladies I work with. So she's on the visible AO camera, and that's what you actually see on the, the true Vis-AO detector side. Okay, and this is just a nice example of the Orion trapezium, which is, I'm sure you guys all know of that trapezium. I've probably imaged it before. So this is just visible imaging of the trapezium cluster with Magellan adaptive optics and how 0.032 arc-second resolution you can get. Now H-alpha binary on this guy. So just kind of an example of what you can do. And this is just due to that thin shell, we have those wind limits. So we always have this page open as well, which, let's see here, let me check that. What is the surface area that the actuator can actually manipulate? I see, okay. So this, I guess, is about, let's see, probably 3 or 4 centimeters, about the palm of my kind of finger on here. And while that's moving, it moves approximately what that magnet on the other side is. So about the same size, that kind of 4 centimeter size. But then it also, it doesn't just push that one exact spot, since there's actuators literally directly next to it. They're not quite touching, but they're within a centimeter of each other. They're all kind of intertwined with each other. So even though it's got just like a 4 centimeter surface area, it really can affect up to a whole quarter of that secondary, since all of them are really working in conjunction. So that's a good question. And was there anything else? No, okay. So this is our weather page. The DIM is a calculation of seeing, which I'm pretty sure is just a C8 telescope out there with a seeing calculator on it or a monitor on it. We also have temperature, wind gusts. That way we always see that real time. And as well as where the telescope is pointing and all that kind of fun stuff. And then where we are down here in Chile. All right. This is, I have never used the visible or the IR camera down there, but if anyone is really into imaging, we can come back to the slide later. But this is about all I know about the cameras. I've been just an operator for the actual adaptive optics side of things. I haven't done any of the actual data collection because the individual who asks for time on our system is really responsible for actually operating the cameras. We just go down to operate the adaptive secondary. They're in charge of, we have a whole website that they have to learn the manuals, and they travel down themselves and they take their data. Kind of like old school astronomers, got to do. Many things are now Q observing, and the observers never actually get to go to the telescopes, which I think is kind of sad. So this is kind of where things, we've talked about all this adaptive optics, a little bit more heavy stuff, and I thought we'd kind of end with how we all got to travel and how the Arizona and Carnegie all work together. But if anybody else has any questions about the actual adaptive optics part, hopefully you have a good baseline of what AO is now. So I'll give you guys a chance to put anything in the chat or ask me any questions. Otherwise, I'll just keep going.
I do have a question.
Sure.
Hi. So why even bother with the secondary mirror? I mean, the issue with this, with the secondary is you want to move it to conform to your flat sensor. Is our issue right now that we just can't, move those pixels around, with like MEMS or something? Is that coming in the future? Is that something that's being worked on, or?
So I haven't worked on MEMS myself, but Katie, actually, this professor right here, she's worked on those type mirrors. I'm still kind of new in the whole adaptive optics world. I haven't had a chance to work on that, but I know there are folks that do work on it, and it is being developed. So we might see it more prevalent, within the next 10 years, because I know it does, that does exist. The secondaries, just at the time, seemed to be the easiest, quote unquote, easy relatively, and most cost effective to actually get some kind of AO correction. But you'd have to ask someone who specializes more in the MEMS world on that. Any other questions?
Yeah, does adaptive optics ever make things worse?
Yes, this is a good point. Yes, it does. So when I talked a little bit about how the AO cannot correct when it's like a 5 arc-second seeing night at the LBT, instead of it's trying so hard, it can actually put too much force on the mirror. So that's why we have that pink purple, diagram of each actuator, because it can actually create its own stresses because it's working so hard. So in terms of actual resolution on the, imaging camera, it looks bad either way if it's trying really hard or if the seeing is bad, but it makes it worse for us and for its own, just for that thin mirror where it's putting more stress on it than necessary. So that's why we end up we turn it off and wait for the seeing to go away. So that's how it can make things worse. Yeah, imaging wise, it's seeing or bad AO correction are pretty much the same thing,
What about clouds? What do they do?
So I wish we could see through the clouds, but they block everything up. So we can't see anything with the clouds. When you have high cirrus clouds though, that can create the illusion of poor seeing. So sometimes on these real warmer summer nights, we'll get those high cirrus clouds. And since we're not, directly outside observing like you would, in your amateur astronomy days, sometimes we're like, well, why is the AO correction suddenly so bad? And somebody will walk outside and, there's high cirrus clouds. You just turn the AO loop off for a few minutes and then let the cirrus clouds pass and you get it back on. So, but anything more than a high cirrus cloud, you lose your light. So you have nothing to correct on. All right.
I have a question. Emily, nice talk, by the way. How does temperature affect any of these operations? In other words, let's say you have, start off at a certain ambient temperature and then a cold front comes through or something like that, or a warm front. Does that mean you have to close shop too under those circumstances?
So it's more the weather associated with whatever front has come in. So if we have a front that has something associated, with really high moisture,
Right.
we actually have a telescope limit of more than 90% humidity, and that's more of a telescope limit that actually isn't set by us. The telescope operators tell us that, so I would have to ask why that limit is. But I think it's more of there's been too many very close calls of, oh, okay, the humidity's rising, oh, but there's no rain clouds yet, and then you wait and you push it, and then we've had many stories of the TO, the telescope operator is scrambling to close everything because now it's starting raining. So I think that's where the humidity one comes in. But the temperature, we have a few fans that keep laminar flow up there and all that mess of all these cables. So that keeps a pretty standard or a pretty stable ambient temperature, at least around the AO software or the AO hardware components. So we haven't ever seen any temperature issues. And I mean, like the LBT can get ridiculously cold at night and we can still operate. And even in the warm weather, we more so have to worry about the humidity. Same thing with actually cold weather with snow. That of course is a problem too. So any moisture, truthfully, just like you guys, you know, when we're doing just regular observing, we don't want lots of dew on the mirror. It's kind of,
Right, right. Okay, thanks.
yeah.
Nice job, Emily.
Thank you. Yeah, so some of your questions are so good. I'm sorry I can't answer them 100%. Especially with the software part. That's I did not go to software engineering school, but I'm kind of learning it as I work on the MAPS program.
Are you planning personally to continue your studies and maybe get a PhD, or are you happy where you are?
I'm happy where I am so far, but we'll see if that changes. All right. Well, I think I'll talk about, I'll continue a little bit here on kind of the fun side of astronomy, getting to travel. And we haven't done it in over a year, but I still got lucky enough to do it right at the very beginning of working for Steward. So in November, I spent pretty much almost the entire month down in Chile. And just some of the folks you'll see, Amalie Vaz is this lady here. She's kind of my boss, I guess. She's kind of a career AO operator. She's just a bachelor's in, I think, physics, pretty much just like I am. Never decided to do masters. But these two are Jared Males and Katie Morzinski. They're both PhDs at Steward. And Katie is actually the principal investigator for the MAP system. So I work with her pretty much every day getting that ready. And Jared, who just happens to be her husband, so they get to work together on stuff all the time, was Laird Close's grad student. And his PhD project was the VisAO camera. And Laird was basically the brains behind the whole Magellan AO system. And he's this guy right here. So the way the Magellan Consortium works is that it's just a whole collaboration between these 5 schools, which University of Arizona is lucky enough to be part of. And this is just one of the group shots while we were down there. So to give you an idea of how far away it is, Las Campanas Observatory is about halfway up Chile. And of course, here we are in Arizona. It's actually the Atlantic time zone. So before we go, we had to basically 30 days in advance, got travel authorizations, got our airplane tickets all settled out, any financial advances that we had to get for those tickets. But during our visit, I don't know if anyone was following the Chilean news, but in the middle of October, the Chilean protests began, and we were actually very nervous that we would not be allowed to go because the telescope workers, so to give an idea of how telescopes actually have their day-to-day operations, they don't go up and down the mountain every day because most of them are at remote sites, just to you'll see how remote this site is. So they have week by week shifts. So the Tuesday, for whatever reason, is the astronomy shift change day. So at least for the LBT and for Las Campanas, every Tuesday they have a new shift come up to the mountain. And the observatory vans for transporting were getting targeted because they were, a financially healthy institution. They're an academic institution. It's not fair. So they had to be very careful. And there were at least 2 shift changes that actually couldn't happen because they couldn't get the workers back and forth. Luckily, they're very well stocked at the observatory where they had food if they had to stay that long. But for a little while there, it was looking like we wouldn't be able to go. But we still had our flights. These are actually the returning flights. So it's a 3-flight ordeal. So first day I just Ubered to Tucson. You take a Tucson to Dallas flight, sit there for a little while. And then you take the all-night flight on an absolutely beautiful 787 from Dallas down to Santiago. And back then we were served dinner and breakfast on the airplane. It was great. And then just the nature of how we got into Santiago, we had to sit at Santiago Airport for 6 hours until we could get our one last flight north to La Serena Airport via their LATAM Airlines. And if you've never traveled to a foreign country, English is still listed. It's just listed second. These are the Andes Mountains out in the distance out there. This latitude is very similar to Tucson. It's very desert-like, dry. It does have mountains. A little different than Flagstaff because it's a little bit drier there. Just another image of what the mountain ranges look like. Let's see. And then when we landed at La Serena, this was just such a like mind-blowing experience. Here we are on like, I think it was an A319, and we literally turned off the runway, probably taxied about 10 feet and stopped. I mean, it was the fastest taxi I've ever had, even flying out of a tiny airport back at home. That was the fastest taxi ever. It was just such a bizarre experience. And then they just let us off. Kind of was like no head counting. They just were like, all right, go ahead, go to the terminal. So that was a bizarre experience. It almost looked kind of like a half resort, half construction zone. It was different. So now, normally we could just hail any random taxi that would take us to the downtown La Serena offices, which is called El Pino. And it's just called that because of there's one pine tree. But they had to actually arrange our taxi driver to make sure he was vetted and was not part of the protests. So he was very nice, Patricio. He had about 20, this image isn't great, but he had about 20 Snoopy bobbleheads on his dashboard. So he made us all feel very safe, even though it was kind of, you were driving by, there was absolutely no traffic lights anywhere. They were all on the ground, shattered. And graffiti everywhere, people rioting literally as we were driving through. So, but he made us feel very safe. I'm glad we had him. And so we just were waiting there maybe 10 or 20 minutes for him to show up. He took us to the El Pino area, which I couldn't take too many pictures of because they wanted us kind of in and out so that we wouldn't get followed by anyone. So we just checked in, we got some water, and they were nervous that they wouldn't be able to get a whole lot of food up there. So they actually stuffed the trunk of the taxi with bread. Normally there would be, regular food trucks that bring in fresh food. And we would normally take a Las Campanas Observatory van, but we actually had this poor taxi driver drive us all the way from La Serena up to the observatory, which was another about 3 hours. So now we've already been traveling about, let's say, I think the whole trip took 29 hours of traveling to get there. And this is actually the El Pino downtown offices just have little rooms that we could stay in. So on the way back, we were able to take like a nap here instead of having to sit in the airport in the terminal at La Serena. Okay. This is just what the drive looks like up there. It's very desert. They still have windmills. It's desert mountains, kind of just like Tucson is actually. And actually before this it's called the Pan American Highway. Before that road existed, they used to actually get on a fourth flight from La Serena to this airport that's on the base of the mountain. And then from there they would get driven up. But that has since they've built this highway, they've stopped doing that. But like when Laird first started even scoping out Las Campanas, they would take like a little mini turboprop airplane or a twin Cessna and to get up there. And this was the first sign for the observatory. Finally, it was kind of nice to actually see one. You can barely see it. It's out there in the distance. These images aren't fabulous, but there's a little white dot there of the observatories in the distance. At the base of the mountain, this was a normal checkpoint where they all check our IDs to make sure that we weren't, crazy people trying to drive up the mountain. And they checked all of our luggage, but it was all bread in the trunk. So we were allowed through, luckily. So the observatory road is pretty typical of other observatory winding, dirt roads all the way to the top. You just barely start seeing the dome. And this is where the Carnegie Institute of Science acreage begins. So I guess that was in the 70s. They bought like a couple thousand acres at like a penny per acre. So Carnegie actually owns the land that the telescope is on, which is also unusual. Most of the time, observatories just lease the land that they're on. So the fact that they own it and they can control all of it, that's why there's no, squirrel permits or anything, unlike the LBT. Okay, all right, so then we get to the mountain. There is a nice little lodge there, and we just have this TV that has our room assignments on it. So we were up in the B2, and these are all the workers that come up, week by week. Okay, and this is what, it just almost looks like a little hotel room door, to the outside. And this is what it looked like right outside. my door, so you can actually see the twin telescopes here, the original telescope, the DuPont telescope, and I think there's a Polish telescope here, down the hill a little bit. These are like the observatory stockpiles, and there's a little mini medical center over there if you needed something. And this is like the astronomy shop, and there's a library, there's a clean room in here. This is what our rooms look like, just like a regular hotel room, pretty much. So they give us really nice accommodations. We have our own restroom, which if anyone has ever been to, I've spent the night at Mount Wilson, and those rooms are like triple bunk bed rooms, and you all have to share the same bathroom. I mean, it's kind of cool to think, ooh, Hubble slept in this room, but it's also nice to have our own room. And the shades come down and are completely blackout shades. That way, you know, we have to sleep during the day when we're observing. And I slept really well during the day there. I didn't have any issues with the light coming in. This is just what it looked like at sunset that first day. We actually arrived on a day it was cloudy. I couldn't believe it. I thought I had brought like my East Coast bad luck weather with us all the way down to Chile. But it just looks like desert. It's very dry. This is around 8,000 feet. So you're feeling a little bit of the altitude, but not a whole lot. Nope, try that again. All right. This is just a whole, we don't have to bring our own food. They bring it up for us. I mean, we happen to bring bread, but they have their own, it's not catered. It's actually out, they have a whole kitchen and a nice dining room that just is a larger version really of this. And they cook every single meal for us. It's absolutely delightful. And all the food is, you know, extremely healthy. So I was kind of afraid, oh, I'm gonna, you know, there's so much great food, I'm gonna get all, you know, weighed down, but the food was so healthy. And, you know, they cooked us fish that was probably just caught right off the ocean out there. And they gave us cheesecake, and it was excellent. I would eat that food for the rest of my life if I could. And then at the actual domes, they have these little cookie and cracker cupboards. So you can snack a little bit through the night. That was like the only junk food that we were allowed to have. And then when you're on night schedule, you have to fill out this night lunch form where you can either get, just have them plate up, like Katie had them plate up some soup and a plate of dinner, or you can just check mark what kind of sandwich you want. And then it's the telescope operator's job to actually bring your night lunches up in this little, you know, blue shopping basket, and all your sandwiches are all wrapped up. So food, don't have to worry about it. You're taken very well care of. There's also a lot of wildlife there. So during the like hour or so before sunset, when I would have to go start setting up, I would go for walks. And I actually got to see a herd of wild horses running in the desert. I felt like I was in a movie. So there's just a little herd of horses. And then there's burros absolutely everywhere. This was literally right next to the road, walking up to the telescope. They're just looking at you. Sometimes they're actually squaring up with you, trying to, you know, protect their herds. You have to actually be very careful. You have little foxes that are just wandering around. And all these squirrel rabbit looking things are called viscachas. And they are pretty much as cute as they look. They've got these little tails and giant ears, but they just kind of hang out up in the beam supports of the clean room area. These have actually gone into the dome kitchens and have eaten the cookies and crackers. So there's like signs all over the place, keep your doors shut. So they cohabitate with their wildlife there. It's very nice. This is what the kitchens up at the dome look like. They'll have, you know, coffee, which is kind of what you live on when you're up all night, and you know, cereal. And there's a little lounge room if you want to take a nap, but half the time you get pretty acquainted with being up all night, and you do okay staying up all night. All right, this is what the science camera and the telescope operator stations look like. Just to give an idea, this is what the telescope operator is sitting out watching. The weather is the first thing really sitting in front of him. And he's got tons of screens to watch what his active optics. So that's a little bit different than adaptive optics. So when you first point the telescope, the active optics, they're very similar. They're just much larger actuators, and there are very few of them compared to the tiny actuators. Just to counteract how giant that mirror is, you know, 6.5 5-meter mirror. So that's what active optics are. They just adjust for pure gravity astigmatism that gets introduced. And then this is Alicia, one of the Carnegie workers. She was just sitting. This was the cloudy evening, that first evening. Everybody else went to sleep, but I went and snuck up to the dome and got to hang out with these guys a little bit. So this is the view looking at the telescope at the summit for the Clay and the Baade telescope. It's about half a mile. So the room that I stayed in is this edge one. So you just would walk up the hill. It was like the only exercise we really got was walking up and down the hill. They did have cars that we could have used. There weren't a whole lot of extra ones. So unless you really needed to get up and down real fast, we typically we all walked back and forth. And this flattened peak up here is actually the site of the GMT telescope. And one day we tried to drive down there to just get like a peek to see what it was like, but there were people actively working on it. So they asked us to please leave. So there is progress being made on the site, which is good news. Okay, so now this is after our first sleep, now it's still daytime and we have to begin getting the equipment ready. So we at least get the science camera ready for the observer. We don't take the data for them, but we at least get we have to bring it down to 73 Kelvin, so get it cooled off, get the computers woken up, because this only goes on the telescope pretty much twice a year. So every 6 months we would normally, in non-COVID times, go down, set everything up, and then it all comes back off the telescope when we leave and some other instrument, gets put on. So let's see. This is where the wavefront sensor is housed. They call it the NAS just because it goes on the NASMith port. This is just the giant computer housing for the science camera. And the ASM, the adaptive secondary mirror, is kept in the clean room, saran wrapped like this, and it's kind of 0G for it holder. And this was probably the most nerve-wracking part for me, at least of the whole 2 weeks I was there, was that you have to roll this onto a flatbed truck and actually drive it up to the telescope. And if you have even a little bit of wind, this is just, and we strap it down really well, but it still was a little nerve-wracking walking behind this thing, making sure no straps were getting loose or anything abnormal was seen while we were driving it up. Okay, and then everything gets brought up to the basement of the telescope through this lift from the bottom up. So this is us bringing up the camera, pushing the NAS over. So we spend really the first 2 days actually getting things on the telescope. So this is all daytime work. And we have help from the mechanics that are at the telescope as well. They're trained to know these operations, and they've taken it on and off the telescope probably maybe 24 times now, I would say. They've probably had that many runs. So here, this is just the pump room for actually the telescope. So this is just the pure size of the hydraulic pumps that keep everything running for the telescope. And our glycol cooling pump was down here by Laird's Foot. And this is down in the basement. So if any of you have an LTAS telescope that has to experience a cord wrap problem, this was the most extreme version of cord wrap I had ever seen. All of this is cord wrap management, essentially, going all the way up, spiraled out. And I'm sure someone will ask at some point, because it's a pretty logical question to ask, is there's 2 telescopes, they're twin telescopes, can they be used as an interferometer? So in the basement, they do have the tunnels. So this is the tunnel going to the other telescope. And then where we're standing would be where they get brought together. But they, for whatever reason, never set it up. We're not quite sure why, but as you can see, it's all storage. It's not used as an interferometer, but it was designed that it could be used as an interferometer. Okay, so this is what the NAS looks like, and with Clio, that's the black box on the back side of the NAS. We have a nice Mag.io Arizona license plate that made it all the way down there. And the telescope has to get tipped down to 2 degrees for the ASM to actually be put on. So this is the back side. Let me pause that for a second. all these doors are where the active optics for the telescope are. So that's what deforms the primary mirror due to pure gravity. And this is what the two bearings look like on the side, altitude bearings. So this is the back side of the primary for the main telescope. Just kind of was an interesting view of the whole thing, how low to the ground it gets. And you have stairs going to each side for the NAS platform. It's very loud in the telescope. Everybody's kind of yelling. He's got just a normal hand controller. Tipping the whole thing over. One thing that was a little difficult, at least for me, not being a Spanish speaker, is the mechanics, their main language is Spanish. They know quite a bit of English, but to help them and kind of work with them, you had to learn a little bit of Spanish that they don't teach you, in your Spanish, regular Spanish classes in high school and all that. Okay, so here are videos of using the dome, the crane dome, to bring it to the one spot on the walkway that you could actually install it. So you just have a gate here to get the ring all the way onto the telescope. And this is, once it's on, Laird and I were up actually attaching the glycol loops and any leftover cables on the very top of the secondary. And we use bright pink cable ties so I don't forget any of them. We can see them all. Does that again. And now they've added, all this extra equipment. And just like we balance our telescopes that we like to observe with, we just use our hands to balance the telescope. Now they have it tipped all the way over to, I think, 2 degrees is what they had to tip it down to. So the lead mechanic is literally just moving it by hand to balance it, which I was just shocked when I saw them doing that, but I guess it makes, for the best balance. Now there are mirror clips for the primary, which is, back here. Essentially he's staring at it, the primary. If he had pulled that down any farther, I think any lower than 2 degrees, the clips just can't support the weight of the primary anymore and it would come out. So they've had this down to a science for quite some time. So now that you've gotten it on the telescope, that second day of installing all day, and then you go directly into your first night of observing, is a true 24-hour work straight day. This is what it looks like to have all of the software GUI set up for control. And this was the lowest seeing that I got to see, 0.51 arc seconds. And this is zenith corrected, so it is technically, it probably was a little bit worse, but I've heard stories of like 0.2 arc seconds seeing, but this is the lowest that I saw while I was there. So this is a room just off of the dome. So if we had any issues that we thought, oh, maybe there's a glycol leak, which has happened before, we can just run up half a flight of stairs and be directly in the dome, which is really nice because other observatories like the LBT, you have to take an elevator just to get to the mid floor to see anything going on. So it was nice to only have half a floor to go up to. So this is just during closed loop. So this is kind of watching the actuators respond to the seeing, watching the peak mirror force. We really never wanted to see it spike up to 0.8. If we saw something like that, you would want to turn the AO loop off and check everything. I think this is just another view of it. You can almost get sick from watching it for too long. Sometimes it gives you like motion sickness with your eyes if you stare at it too long. But that's what we're looking at all night when you're in closed loop. I didn't take a whole lot of pictures of what the Clio and VisAO cameras actually looked like, but they had some binary system that they were looking at when I happened to take these images. And this is just in the IR camera, and this is in the VisAO camera. And they actually are able to see when the loop is closed, which is great. That's and in their software, once they put it in a FITS header, they actually have an indication of, okay, this was a closed loop image, so they know if it looks bad, it was probably because the loop was open. and they can throw that image out. Okay, so after, yeah, we kind of talked about that already. After the day or so, it's all, now we're just on night schedule the entire time. So that first evening, you spend basically 24 hours of installing and then working, and then you go to sleep for the first time during the day. Don't forget to fill out your night lunch form and stuff like that. And you're basically night schedule for the next 14 days. And we have this kind of silly tradition to watch sunset, to look for green flash every night. And then we get set up for the evening. And I typically woke up like shortly before the dinner time period. So we had a breakfast, lunch, and dinner that was always at the same time. So you were having a lot of like soup and chicken and turkey for breakfast, but you get used to it after a little while. And then we start setting up about 30 minutes before sunset. We stop to watch sunset, and then we start taking data once twilight has gone down. And once things kind of settle in and the seeing is nice and we have no software problems, or sometimes the telescope had a few hardware issues, but it's pretty quiet up there. You have basically anybody at the science camera, our telescope operator, and then this was our AO station. So it's just this kind of small operating room, but the kitchen was directly below us, and then the dome was basically at this wall. So everything was very accessible. Just more images of what the GUIs look like. We have other, you have the fast mirror GUI, which is giving you a real time, and this was giving you a slower update of what the actuators were doing. So it was helpful, but not, it wasn't giving you constant, like this one is updating constantly. Wavefront sensor control, so you can kind of actually update what the loop frequency is doing on this one. This gives you the observer, what the institution was, what the object is. And we're also filling out kind of like an electronic logbook of everything that we've taken. Okay, so now we've done, let's say, I think it was 10 nights of observing. And then you have a nighttime where you go directly in the daytime. You get like a 30-minute nap in that lounge downstairs. Then you have to take everything off. So just like we had to take, put everything on when we got there, we have to remove any remnant of the MagAO system. So this is what the wavefront sensor hole, leaves behind, just the NAS port for the next instrument to go on. This is looking directly at the primary. So these red doors would fold up and open, and the primary would be right here. So this is essentially standing at prime focus when it's tipped over at 2 degrees. Very bizarre image in some ways. And of course, you've got to take your inverted, secondary mirrors back down in the holder image before you wrap it back up in cellophane and put it back into the clean room. Okay, so here's a video of
Someone else should hold
taking
the
it
other
off.
side. Like,
They let me stand up at the platform when we took it off. So it's just on this L bracket. That you slowly take these shims out and use the crane to back it out, and then use the dome to rotate it around. A lot of spots where you can pinch your fingers. And then this image is just the 2 Magellan systems. This is our MagAO, and this is Jared's MagAO Classic system. So you can see the size of the this is really an optical bench, this black thing behind these guys. So they're still working on getting it operational. So they spend a lot of time in Chile working on it before COVID. And then during COVID, they decided to actually ship it back to the United States to work on it here, so that it didn't just sit there, collecting dust. And then traveling home, we just do the opposite. You get on your LATAM flight, once again, the fastest taxi out to the runway. You get your cool Chile, passport sticker. This time, on the way home, we were actually able to go into one of the observatory vans. It was a little bit more comfortable. And these guys are so funny. This is their probably 100th time visiting, and every time, I guess their tradition is to get greasy, junk food, since the observatory food is too good for you. So that was the very first stop at the airport, was to get some French fries. And then we're home. So these are just some science results to kind of close up our talk. This paper here you can look up, uses MagAO data, and it's the data on the microjet of the Orion Nebula, so you just barely see it. So these are just examples of what our adaptive optics gets used for. And then Kevin Wagner did this great paper about the spiral arms and a protoplanetary disk around the star. So that's just an example of what kind of papers get published with adaptive optics. To close everything up. So I think that's my last slide. Yeah, so if there's any questions, I'd be happy to take them.
There's a question in chat.
Let's see. Actually, stop the share here. Let's get to the chat a little easier.
Quite the presentation, Emily.
Yeah, it was
Thank
great.
you.
Yeah.
How is electricity produced, electrical transmission, local generators? So everything is plugged into the UPS of the telescope, basically. So it's all plug and play, essentially. You know, it's not, there's no external transition or local generators. But that's a good point. I should probably include that somewhere, that we do have a UPS plug-in for everything.
Is this just for stars, or do you do nebula, planetary, anything like that?
It's typically up to the telescope allocation committee, what has the highest priority. I've seen that it's mostly protoplanetary disks and then stars that have proposed exoplanets around them is the majority of what we observe. Sometimes we're looking at Wolf-Rayet stars, but I haven't actually experienced anything with nebula yet. And
I have a question.
Yeah.
Two things. I think one of the reasons why the interferometer option has not been used, I think with optical interferometry with big telescopes, I don't know of any observatory that has been successful at doing that, including, I remember visiting the European Southern Observatory when I was in Chile a few years ago, and they were still trying very hard to just get things coherent between two of the giant scopes, and they could never do it.
Yeah.
It's very, very difficult, I guess. And the greater the distance between the two instruments, I guess the more complicated it gets.
Yeah, so of course the LBT was basically designed to do that, right? So there's a main instrument on that telescope that uses the adaptive optics called the LBTI, which is just Large Binocular Telescope Interferometer.
Yeah.
And that has so many problems. I think we've only done one observing run in the whole year and a half where we had actually both sides operating, you know, both secondaries worked. The beam combiner was actually correctly at vacuum. We've had tons of vacuum leaks just trying to get the beam combined. So you're correct. It is very difficult. Even
interferometry with light at that short wavelength is apparently very difficult, right? Unlike radio astronomy, where it's easy to do.